Let's have a second example for the slowly varying potential. Slowly varying potential. For example, and the potential has the exponential eta t v, and eta is positive. So, and the potential is not time dependent, but here exponential eta t means that slowly varying and slowly changing the potential. Then here our purpose is to calculate C and T. That is n psi t. That is 1 over I h bar, and the integration from minus to infinity to t dt prime, and here, and the potential can be n v 0, and also exponential I epsilon n minus epsilon 0 over h bar t prime, and also because here potential is the exponential eta t prime. Because this is time independent, and we do not consider for the integration. Integration apply to here. Then it is that 1 over I h bar, and integration of this one eta plus I epsilon n minus epsilon 0 to h bar exponential eta t prime, and exponential I epsilon n minus epsilon 0 over h bar t prime from minus infinity to t prime case n v 0. From the minus infinity means that here it is 0, so only the t applied here, and also so I h bar cancel, so epsilon 0 minus epsilon n plus I h bar eta, and here n v 0, and exponential here eta t plus I epsilon n minus epsilon 0 t over h bar. So probability is that C and T square. So by multiplying the complex conjugate, and the epsilon 0 minus epsilon n square plus h bar eta square and n v 0 square, and exponential complex exponential equal to 1, so exponential 2 eta t. So transition rate is that 0 to n is that ddt and pn t. So it is epsilon 0 minus epsilon square plus h bar eta square and 2 eta exponential 2 eta t and n v 0 square. It is time derivative. So in the case for the If the eta equal very small, if the eta is very small, and this exponential, it becomes 1, and also this one makes that in this case, if the eta equal to very small, then this term makes that 2 pi over h bar. So it is 2 pi over h bar and n v 0 square Kronecker delta epsilon n minus epsilon 0. That is for very small eta case. And anyway, then here transition probability can be calculated by multiplying n psi t cnt square, and also transition rate is the time derivative with the transition probability. Okay, then here it is first order correction, but here let's think about that second order perturbation case. Second order perturbation case. This case should be considered that in the case that interacting potential, this term equal to 0 case, and we should consider for the second order perturbation. And basically, and we already calculated the C and T in the second case is that 1 over I h bar square 0 to t, t0 to t, dt prime, t0 to t prime, dt 2 prime, and vit prime and vit 2 prime I state. Then this one can be calculated 1 over I h bar square t0 to t dt prime, t0 to t prime, summation with m, n vit prime, m vit 2 prime I state, and also dt 2 prime. Because let's apply that potential is the time slowly varying potential. Let's apply this slowly varying potential. Then this one makes that 1 over I h bar square t0 to t dt prime and t0 to t prime dt 2 prime and summation with n. Here let's denote that this one is vnm and the exponential I omega n m t prime, because and it makes that vi is that the exponential I h0t over h bar and v exponential minus I h0t over h bar. So and it makes that omega nm t prime. Also here, because it is a time varying potential epsilon eta t prime, also v mi exponential I omega mi t 2 prime exponential eta t 2 prime. Then 1 over I h bar square t0 to t dt prime summation with m v n m v m I exponential eta plus I omega n m t prime, and also exponential for integration with the t2 prime case is that eta plus I omega mi exponential eta plus I omega mi t2 prime, and t2 prime equal to from minus infinity to t prime. So it is 1 over I h bar square. For simplicity, and t0 let's denote that minus infinity to t dt prime summation with m v and m v m I, and also here, and minus infinity, it makes that here equal to 0, so it is a zero term, and also t prime. So eta plus I omega mi exponential 2 eta plus I omega ni t prime, because here omega nm plus omega mi means that epsilon m minus epsilon n minus epsilon m plus epsilon m minus epsilon I, so cancel each other, so it is omega ni h bar over h bar. So finally, and integrate with the t prime 1 over I h bar square to the m integration eta plus I omega mi v n m v mi integration 2 eta plus I omega ni exponential 2 eta plus I omega ni t, because minus infinity also 0. So it is the C and T in second perturbation. So, and transition probability to n to m is that C and T square is that 1 over h to the 4, and by multiplying the complex conjugate, and it is 4 eta square plus omega ni square to the exponential 4 eta t, and summation to m eta plus I omega mi v n m v mi square, and this exponential equal to 1 because complex conjugate, and it is just complex conjugate term. Here anyway, here it is not multiplication of the complex conjugate multiplication, because the summation m applied on all these ones. So after making the summation for all the m, and we should make a complex conjugate square. So then this one is that for h to h bar g bar square. Yeah, omega ni means that h bar square omega epsilon n minus epsilon I square. So h bar h to 4 eta square plus n epsilon n minus epsilon I square exponential for eta t in summation with m okay. Let's apply to the h square here. H square insert here. H square insert here. It is not h square because in the h bar square it is h bar to the 4 and h bar square, but h bar square applied this square term. So it is h bar eta plus I omega I minus omega m. And V and M means that NVM, MVI to the square. Then transition probability, transition rate in the second perturbation to NM transition rate in the second perturbation is that limit eta equal to 0, and for very small eta ddt and p nmt time derivative. So it makes that in a similar manner, and also the factor 2 pi over h bar, and for summation to m epsilon I minus epsilon m plus I h bar eta n v m m v I to the square in correct delta epsilon n minus epsilon I. So it is second order perturbation case. And basically, in the second order perturbation case is that by calculating this one, and the interacting potential has a double. So, and here VIT becomes like this. So it is exponential VNM and I omega NMT prime. It is a slowly varying potential. If we apply the slowly varying potential like this,